Good evening, everyone. Am I audible to everybody and is the screen visible?
Yes,
Okay,
the screen is visible and you're audible.
okay, thank you. So, we will begin with today's session. And good evening, everyone, and I welcome myself. I am Abhik Dev, a PMRF PhD scholar in the Department of Mechanical Engineering at IIT Bangalore. And I shall be dealing with the live sessions of the course wherein we will be solving some of the problems related to the concepts discussed in the previous week lecture of the class, so as to help you with the problem solving skills and also to help you clear some of the doubts related to the concepts that were discussed previously. I request all of you to be present every Friday from 6 to 8 p.m. to make this outreach a success. uh, Without further delay, let us start with today's session. Today we shall be discussing problems related to some of the equipments and devices, their energy analysis and their entropy analysis, and then we shall be moving to an introductory concept of the basic Rankine cycle for that is used in the steam power plant. uh, so uh, okay, let us begin with the problems related to equipments and devices first. So, the first problem: a steam turbine receives steam at 6 megapascal, 800 degrees Celsius. It has a heat loss of 49.7 kilojoule per kg and an isentropic efficiency of 90%. The exit pressure is 15 kilopascal and the surroundings are at 20 degrees Celsius. The actual work between the inlet and the exit is what? And also we have to find the actual change in the entropy of the steam. So, mm, what is the process going on here? Okay, so this is a steam turbine. Let me draw a turbine first. Okay, so this is the inlet at state point 1, this is the exit and state point 2. Okay, turbine. So at inlet, what is the condition at inlet? Inlet is at 6 megapascal, 800 degrees Celsius. And what is the exit state? The exit state is 15 kilopascal and 20 degrees Celsius. So in the turbine there is a fall in the pressure from 6 megapascal to 15 kilopascal, whereas the temperature decreases from 800 degrees Celsius to 20 degrees Celsius. So this at this 6 megapascal and 800 degrees Celsius, it will essentially be a superheated steam condition. So at inlet corresponding to state point 1, the entropy is 7.6469 kilojoule per kg Kelvin, and the enthalpy is 4123.97 kilojoule per kg. So these properties have been taken from any standard steam property table. So you can follow, I mean, from the based on the property table that we have considered, we have got these values. You can consider any property table from any standard textbook, and it might be just a small variation in the values, but it will be essentially in the same range. And at the exit stage, that is the state point 2, we have been stated that mm, the isentropic efficiency is 90%. Okay, so let us first see that for isentropic expansion process, what will be the entropy. So for isentropic expansion, S2S will be equal to S1, and that equals to 7.6469 kilojoule per kg Kelvin. So if we at this 15 kilopascal at 20 degrees Celsius, if we see the value of SF, it is 0.7543 kilojoule per kg Kelvin, and Sg is 8.0091 kilojoule per kg Kelvin. So this S2S value, it is basically less than Sg, so it will be in a mixture state, that is a mixture of liquid, water and vapor. So the quality of the mixture at the state point 2s, that state point 2s corresponds to okay, let me draw it here. So if we draw it on a TS diagram, so this one, so this corresponds to 6 megapascal, and this corresponds to 15 kilopascal. Then from here, if this is the state point 1, then this, it will come to somewhere here, 2s. Okay, so x2s is equal to s2s minus sf by sg minus sf. So this is, if we put in the values, we will get this one to be 0.951. Okay, so what is the value of enthalpy? Therefore H2S is equal to HF plus X2S HFG. HF and HFG, now this correspond to the saturation pressure of 15 kilopascal. So if we put in the values, we will get this is 225.85 plus 0.951, and HFG is 2373.51. So it comes out to be 2483.06 kilojoule per kg. Now the isentropic, if we have to find out what is for an isentropic efficiency of 90%, what is the actual work between the inlet and the exit. Now isentropic work is W isentropic, this is H1 minus H2S. So this is basically specific work. Okay, this is like kilojoule per kg. So 4123.97 minus 2483.06. So this value comes out to be 1690.91. Sorry, 1640.91 kilojoule per kg. We know the isentropic efficiency is equal to the actual work output by isentropic work output for a turbine. For a compressor, it will be the reciprocal of this. Like so, isentropic efficiency for a compressor will be isentropic work input by actual work input. But for a turbine, it is the actual work output by the isentropic work output. So the actual work is the isentropic efficiency multiplied by the isentropic work. So this is 0.9 multiplied by 1640.91. So this value comes out to be 1476.82 kilojoule per kg. Okay, this is the actual work between the inlet and the exit. We have to also find the actual change in the entropy of the steam. So actual change in the entropy of the steam. Now the actual work is actually equal to H1 minus H2 minus Q loss. Okay, where H2 corresponds to actual exit state. Okay, so if we draw it somewhere here, uh, say this one, so maybe it will be somewhere here. We don't know what will be the actual value, but it will be somewhere on this side like this. Okay, pardon my drawing, so it is a bit difficult. Okay, so we have been stated that in the actual process there is already a heat loss of 49.7 kilojoule per kg. Okay, so in the when there is an actual process from 1 to say 2, there will be a heat loss of 49.7 kilojoule. From 1 to 2 is there is no heat loss, because it is a isentropic process we have considered, and in isentropic essentially has to be reversible and adiabatic, that which means that there is no heat loss. But from 1 to 2, that is when it operates at a isentropic efficiency of 90%, there will be a heat loss of 49.7 kilojoule. So incorporating that heat loss, we can find out what is the value of H2. So W actual we have already found out, so we can find out the exit state, the actual exit state of the steam here, that is equal to this one. So this is 4123.97 minus 1476.82 minus 49.7. So this value comes out to be 2597.45 kilojoule per kg. So if we see the value of Hg corresponding to a saturation pressure of 15 kilopascal, it is equal to it will be equal to around 2600, nearly equal to 2600 kilojoule per kg. Okay, so it will be less than this one. So this will also lie within the mixture zone, that is a mixture of liquid vapor and liquid and vapor. So the quality at the state 2 is H2 minus HF by Hg minus HF. Okay, so it is 2597.45 minus HF is 225.85, and this HFG value is 2373.51. So this value comes out to be 0.9991. Okay, so it is almost equal to 1, but it will still be in a mixture phase. Therefore the entropy at the state point 2 is 1 minus x2 into SF plus x2 into Hg. So this is if we put in the values of SF and SG as we have already used in the first part of the problem, SF and SG, we will get the entropy to be 8.0032. Therefore, the required change in entropy of the steam is S2 minus S1. So 8.0032 minus 7.6469. This is 0.3563 kilojoule per kg Kelvin. So this is the total specific change in the entropy of the steam during the process. Okay. So I hope it is clear to everybody. If there is any doubt, you can ask. Okay. So if there is no doubt, then uh, I will start with the next problem. Okay. So it is a problem of a filling of a tank. So a 25-liter tank as shown in the figure below, that is initially evacuated, is connected by a valve to an air supply line flowing at 20 degrees Celsius and 800 kilopascal. The valve is opened and air flows into the tank until the pressure reaches 600 kilopascal. Assume the process to be adiabatic. Find the final temperature inside the tank. Also find the mass of air that has entered the tank. So the air supply line, this air supply line, it has a air flowing at 20 degrees Celsius and 800 kPa. Okay, and the volume of the tank is 25 liters. Okay, so it will, from the initial state to the final state of 600 kilopascal, it will fill the tank. And initially it is evacuated and finally it has a pressure of 600 kilopascal. The process here is adiabatic. We have to determine what is the final temperature inside the tank and also what is the mass that has entered the tank. Okay, so let us start with the energy equation, or let us start with the mass conservation equation first. So dm by dt of the control volume. So basically we are considering the contents of the tank as the control volume. Okay, so the contents of the tank form the control volume. So this is equal to m2 minus m1, where 2 denotes the final state, 1 is the initial state, and I denotes the inlet state, and E denotes the exit state. Okay, so this is also equal to mi minus me. So for a steady flow process, this will be 0. Okay, so this implies that see, no mass is exiting the tank, so me is also 0. So we can say that, and it is also initially evacuated, so the initial mass is also 0. So we can say that the final mass, that is the mass in the final state, will be equal to what is the mass that is entering the tank. Okay, now in the energy equation, dE Cv by dt, which is 0 for a steady process, this is mi hi plus vi squared by 2 plus gzi, this is the inlet, minus me he plus ve squared by 2 plus gze, okay, plus Q minus W. Okay. Now we are neglecting the changes in the kinetic and potential energies. That is, delta kinetic energy is 0, delta potential energy is also 0. Okay. So in that case, uh, and it is stated that the process is adiabatic, so this is 0. Then we get mi hi minus me he minus w dot is equal to 0. But here no work is also done. This is not any piston cylinder arrangement or any steering work. No work is done. So this is also 0. So we can come to the conclusion here that MIHI uh, sorry, this won't be 0 uh, because the energy is coming into the control volume in the form of mass. So this will also not be 0 because the mass of the control volume is changing. Okay, this basically dmcv by dt, this is equal to mi minus me actually. So and this one will be, this is not 0, this will be final internal energy minus initial internal energy. Okay, so from this we get that m2u2 minus m1u1 is mihi minus mehe. Okay, there is no mass exiting the control volume, so this is 0 and it is initially evacuated, so this is also 0. So this basically gives m2u2 is equal to mihi. But we have initially seen from the mass conservation that m2 equals to mi. So u2 equals to hi. Okay, so at 20 degrees Celsius and 800 kPa, okay, which corresponds to the supply line. Okay, the enthalpy for dry air, that is the air that is flowing through the pipeline, is 293.65 kilojoule per kg. Okay, and therefore u2, that is final internal energy, is equal to this one. Now from the property table, we have been told that the final pressure inside the tank is 600 kPa. Okay, so from property table corresponding to, from property table of air corresponding to 600 kPa, this pressure remains constant. Okay, corresponding to, for internal energy equals to 293.65 kilojoule per kg, we get the temperature of air, uh, temperature of air, temperature of air T2 to be equal to 410 Kelvin. Okay, this can be one of the solutions. Otherwise we can also see that alternatively we can also do it like this. At 600 kPa, the CV value for air, it is nearly equal to 0.718 kilojoule per kg Kelvin. Okay. Why considering CV? Because the entire process is happening at a constant volume wherein the volume of the container remains fixed. Okay. So U2 is basically CV T2. Okay. So T2 can be written as U2 by CV. Okay. Herein we have considered air to be an ideal gas wherein the internal energy is a function solely of the temperature. So this is equal to 293.65 divided by 0.717, sorry, 0.718. So this nearly comes out to be 409.6 or 410 Kelvin. Okay. So this is the final temperature of air inside the container, inside the tank. And what is the final mass of air? The final mass of air inside the tank, this is also equal to the mass of air that enters the tank. This is equal to P2 V2 by R P2. So this is 600 kPa multiplied by volume, final volume of the container. The volume of the container is 25 liter, that is 25 into 10 power minus 3 meter cube. So this is 25 into 10 to the power minus 3 meter cube divided by 0.287 into 10 to the power 3 multiplied by the temperature, which is 410. So the mass of air comes out to be 0.1275 kg. Okay. So I hope it is clear to everybody. If there is any doubt, you can ask. If there is any doubt, you can ask, else we will move on to the next problem. Okay, so let us go ahead with the next problem. A 200-liter tank as shown in the figure initially contains water at 100 kilopascal and a quality of 1%. Okay, so that is 1% is vapor. Heat is transferred to water, thereby raising its pressure and temperature. At a pressure of 2 megapascal, a safety valve opens and saturated vapor. So this valve is stated to open at 2 megapascal. And saturated vapor at 2 megapascal flows out. The process continues maintaining 2 megapascal inside until the quality in the tank is 90% and then stops. Find the total mass of water that has flowed out. Also find the total heat transfer during the process. So what is the process here? It starts with 100 kilopascal. When the valve is closed. Now due to heat, the liquid starts getting converted. It starts with an initial vapor content of 1%. As the liquid starts getting converted to vapor, the pressure increases. Since the valve is not open, so the pressure in the inside the tank keeps on increasing. Okay, it is a fixed volume tank, so the pressure keeps on increasing. The pressure increases till 2 megapascal. Okay, once the 2 megapascal value is reached, the safety valve opens, and this vapor will now be at, this vapor and liquid will now be in equilibrium at 2 megapascal. That is the saturation pressure at this condition is 2 megapascal. So at 2 megapascal, the vapor is being taken out from the container, and the heating process is continued such that more and more liquid gets converted to vapor and the vapor is being pulled out, and this process continues till 90% of the mixture is vapor now. Okay, so in that case, what is the, we have to find out what is the total mass of water that has flowed out, that is what is the total mass of water that has, or steam that has been taken out from this, and what is the total heat transferred during the process. Okay, so we will start with the initial state. X1 is 1%. Specific volume is 0.001043 of the liquid phase, and of the gas phase is 1.69 meter cube per kg. Therefore, what is the specific volume at the state point 1, that is Vf plus x1 into Vg minus Vf. So by putting in the values, we get it to be 0.0179 meter cube per kg. Then what is the mass initially? So the mass initially will be equal to the total volume by the specific volume. Total volume is 200 liter, that is 0.2 meter cube, by 0.0179. So it comes out to be 11.15 kg. So initially 11.15 kg of liquid plus vapor water is liquid water plus vapor is present. At now the by heating process, the saturation pressure becomes 2 megapascal and x2 is 90%. So this is the final quality. The specific volume of the liquid phase is 0.001176 meter cube per kg, and the specific volume of the gas phase is 0.099676 meter cube per kg. Therefore, the final specific volume is 0.0898 meter cube per kg from these values, and the final mass is V by V2. That is the total volume by the specific volume. This is 2.2265 kg. So this is the final mass. Therefore, the total mass of water that has flowed out, therefore mass of water that has flowed out this is equal to m1 minus m2. This value comes out to be 8.92 kg. So this mass of water in the form of vapor comes out of the tank. Now, if we write the energy equation for the process, then dE by dt is equal to mi hi plus vi squared by 2 plus gzi minus me he plus ve squared by 2 plus gze plus q dot minus w dot. Kinetic energy changes and potential energy changes are neglected here. Okay. In this process, there is no work done as well, but heat is being transferred continuously to the process. So this value gives m2 u2 minus m1 u1 is mi hi minus me he plus q. Okay. all in rates. Now, again from the mass conservation, this is equal to mass of the control volume changes from M2 to M1 to M2. This is equal to Mi minus Me. Here, there is mass exiting, there is no mass entering. So this is 0. This implies mass exiting is equal to M, sorry, this will be M1 minus M2. Initial mass is more and the mass is being lost, so the mass of the control volume decreases. This is equal to M2 minus M1. Now, at 100 kPa, with quality of 1% quality, initial internal energy becomes 1 minus 0.01 into 417.20 plus 0.01 into 2505.90, which comes out to be 438.09 kilojoule per kg. At 2 megapascal for saturated vapor, the exit one. In this case, Mi is 0 already. He is Hg corresponding to 2 megapascal, and that is equal to 2797.03. Also, at 2 megapascal with a quality of 90%, that is for the mixture, the internal energy, that is U2, will be equal to 1 minus 0.9 multiplied by 905.94 plus 0.9 to 2597.67. So the final internal energy is 2428.49 kilojoule per kg. Okay. Now, one implies M2 U2 minus M1 U1 is Q minus Me He. Yes, Q is equal to, if we cancel the rays from both the sides, then it is M2 U2 minus M1 U1 plus Me He. So what is M2? M2 is 2.2265. 2.2265 multiplied by U2. U2 is 2428.49. 2428.49 minus M1 is 11.15 multiplied by U1. U1 is 438.09 plus Me. Me is equal to me is the mass that is exiting actually. So so if it is m2 minus m1, that is final minus initial is the change, so then mu will be equal to m1 minus m2. M1 minus m2, and this is actually the mass that is exiting, and which we have found out to be 8.92. So 8.92, and the exit enthalpy is 2797103. So the value comes out to be 25.48 megajoule. So this is the total heat transferred during the process. I hope it is clear to everybody. If there is any doubt, you can ask. Okay, so I am taking that there is no doubt. Then we will move on to the next problem. So the helium in a steel tank at 250 kilopascal 300 Kelvin with a volume of 0.1 meter cube, it is used to fill a balloon. When the tank pressure drops to 150 kilopascal, the flow of helium stops by itself. So from 250 kilopascal, due to pressure difference, the helium starts filling into a balloon, and when the pressure drops in the tank drops to 150 kilopascal, the process stops. The helium balloon is still at 300 Kelvin, and assume that the pressure in the balloon varies linearly with the volume from 100 kilopascal, wherein the volume is 0, to a final pressure of 150 kilopascal. That is, the helium from 250 kilopascal 300 Kelvin in a tank of 0.1 meter cube is used to fill a balloon which starts from a initial volume of 0, and a pressure of 100 kilopascal to a final pressure of 150 kilopascal, wherein the tank pressure also drops to 150 kilopascal, and during this entire process the helium remains at a constant temperature of 300 Kelvin. What is the final volume of the helium balloon? Now, here we take the tank and the balloon as a control volume. We take tank plus balloon as a control volume. Okay. Initially, the pressure is 250 kilopascal. Initially, it is P1. Initially, there is no volume of the balloon, so it will be at, the helium initially is just at 250 kilopascal pressure, and there is no helium in the balloon. So we are not considering 100 kilopascal. We are seeing that the moment it starts to fill the balloon, the pressure starts from 100 kilopascal and it increases to 150 kilopascal. But before, at the initial point, there is nothing inside the balloon, and the entire helium is inside the tank at a pressure of 250 kilopascal. So it is P1 is 250 kilopascal. Initial volume is at 0.1 meter cube. Since the balloon has no volume at this point, and the temperature is 300 Kelvin, and finally the helium is at a pressure of 150 kilopascal. How? Because inside the balloon also and inside the tank also the pressure becomes 150 kilopascal. The final volume is, we don't know what is the final volume of the system, and the final temperature is also 300 Kelvin. So it is basically a constant temperature process. So for this process, for this system, uh, let me uh, uh, rather write it as the system. We are now taking it as a system. That is mass of helium is taken as system. For this system, so the mass doesn't change. Mass in the initial stage is equal to the mass in the final stage. So that is P1 V1 by RT1 is P2 V2 by RT2, considering the helium to be an ideal gas. So T1 is equal to T2. So V2 will be equal to P1 V1 by P2. So if we put in the values, we will get this is 250 by 150 into 0.1. So this is 0.167 meter cube. Okay. Now the tank. So this is like the tank, and this is the initially the balloon. Okay. Two. This is the tank, and this is the balloon. Okay. So this volume, sorry, this volume was initially 0.1 meter cube, and this total volume now is 0.167 meter cube. So what is the final volume of the balloon? So the volume of the balloon will be this. This is the tank is rigid, so its volume doesn't change. So since tank is rigid, so final volume of the balloon is 0.167 minus 0.1, that is 0.067 meter cube. Okay. So in the previous problem, we have to find what is the heat transfer during the process. So now we are considering the tank, okay, and the balloon as the control volume. This is the control volume. Okay. Here the mass m1 is equal to m2 is equal to m. That is, no mass is exiting the control volume, and mi is equal to me. No mass is entering or leaving the control volume. So for the balloon, pressure varies linearly with volume, and V is equal to 0.1 meter cube the pressure is 250 kPa, and at V is equal to 0.167 meter cube, the pressure is 150 kPa. Therefore, from this, what we can write, pressure is 250 plus 250 minus 150, like we are writing an interpolation for this for any intermediate volume, 0.1 minus 0.167. For any intermediate volume V, the pressure will be this. So this is basically 250 minus 100 V minus 0.1 by 0.067. Now the work done in expanding the control volume uh, so the work done in expanding the control volume is integration PdV. So this is from 0.1 to uh, 0.167. So the volume of the system, control volume, increases from 0.1 to 0.167, and the pressure is related to volume as 100 by 0.067 V minus 0.1 dV. So if we simplify it, 250 0.167 minus 0.1 minus 100 by 0.067. So this will come out V square by 2, that is 0.01 0.167 whole square minus 0.1 whole square by 2 minus 0.1 multiplied by 0.167 minus 0.1. So if we simplify it, the value will come to 13.4067 kilojoule. So this is the work required for the filling of the balloon. Now from the energy equation, dECV by dt, that is m2u2 minus m1u1, this is equal to mi hi plus vi square by 2 plus gzi minus me he plus ve square by 2 plus gze plus q minus w. Okay, so there is no inlet or exit here in the control volume, so we will get that q equals to m2u2 minus m1u1, and since m2 is equal to m1, so this can be written as m u2 minus u1 plus w. So what is the work done? Work done is 13.4067 plus mCV T2 minus T1. But this T2 minus T1, there is no change in temperature, so this is 0. So this will essentially be equal to the work done. So this is 13.4067. So the heat transferred during this process is 13.4067 kilojoules. Okay, so I hope it is clear to everybody. If there is any doubt, please ask. If there is no doubt, then we will move on to the next problem. Okay, so I'm taking that there is no doubt, then I will move on to the next problem. So it is a mass loaded piston cylinder assembly. Uh, contains air at 300 kilopascal and 17 degrees Celsius with a volume of 0.25 meter cube. So initially the volume is 0.25 meter cube. While at the stop, so these are the stops. So when the piston moves to this point, because of the supply of air into it, the volume is 1 meter cube. An air line of 500 kilopascal and 600 Kelvin is connected by a valve that is then opened until a final inside pressure of 400 kilopascal is reached, at which point the temperature is 350 kilopascal. So from 300 kilopascal, 17 degrees Celsius, and volume of 0.25 meter cube, it takes in air which is at 500 kilopascal and 600 Kelvin, and it reaches a final pressure of 400 kilopascal, wherein the volume becomes 1 meter cube and the temperature becomes 350 Kelvin. So we have to find out what is the mass of air that has entered the cylinder from the air supply line. So uh, so in the piston cylinder assembly, initially the pressure is 300 kPa, P1 is 17 degrees Celsius, and the volume is 0.25 meter cube. So the mass is P1 V1 by RT1. So 300 into 290, sorry, 20, 0.25 by 0.287 multiplied by 290. So the mass is 0.9011 kg. And finally, the pressure is 400 kPa. The temperature is 350 Kelvin, and the volume is 1 meter cube. Therefore, the final mass is 400 multiplied by 1 divided by 0.287 into 350. So this is 3.982 kg. Okay. So the mass entering the cylinder is what? Therefore, mass entering the cylinder is equal to m2 minus m1, that is equal to 3.081 kg. So this is the answer to the problem. Now in this problem we have to determine what is the total work done and the heat transfer. Now during the movement of the piston in the piston cylinder assembly, initially there is a constant from here to here. As the piston moves from this 0.25 meter cube to 1 meter cube, it is a constant pressure process because there is nothing restricting the movement of the piston. So it is a constant pressure process, and wherein the volume increases with the increase in the temperature. So after the piston reaches the stop, uh, another process will start, in which it will be a constant volume process, in which the pressure will increase from 300 kilopascal to 400 kilopascal. So initially it will be a process in which the pressure remains fixed at 300 kilopascal and the volume increases from 0.25 meter cube to 1 meter cube. After that, the pressure after that the volume remains constant at at 1 meter cube, and that pressure increases from 300 kilopascal to 400 kilopascal. Okay, so uh, so during the movement of piston, In the piston cylinder assembly, initially there is a constant pressure expansion process. Pressure expansion process. Pressure is at 300 kPa, wherein the volume increases when wherein volume increases from 0.25 meter cube to 0.1 meter cube. Okay. Then there is a then the volume is held constant at 1 meter cube, and pressure increases from 300 to 400 kPa. Okay. So work will be done only during this process. Work is not done during the constant volume process. Therefore, the work will be done only during the constant pressure process. The work done is P delta V. So pressure is at 300 kPa, and the volume changes from 0.25 to 1. So it is like 225 kilojoule. Okay, so this is the work done during the process. And what is the heat transfer during the process? So from the energy equation, if we write, okay, m2u2 minus m1u1 is mi hi minus meh plus q minus w, neglecting the changes in the kinetic energy and the potential energy. So work done we already know. Heat transfer we have to determine. And in this process, uh, there is nothing exiting, and mi basically equals to m2 minus m1, and this value is equal to m2 minus m1. So the heat transferred is equal to w plus m2u2 minus m1u1 minus m2 minus m1 to hi. So if we put in the values, plus 3.982 into u2 we are writing as cvt2, so this is 0.717 into 350 minus initially mass is 0.901 into 0.717 into 290 minus 3.081 into 1.004 h1 hi we are writing as cpt, so this is 600 and exists at the inlet condition. So this value comes out to be 819.05 kilojoules. So there is basically a heat loss for the system. Okay, so this is the heat transfer during the process. I hope it is clear to everybody. Now we will be, if it is clear, then we will be moving on to problems in which we will be using the concepts of enthalpy and entropy to a cycle, like the components of a cycle. Okay, so let me know if there is any doubt, otherwise we will move on to the next problem. Okay, so if there is no doubt, then we will move on to the next problem, in which so this is basically a problem of a heat pump system, in which we will be now utilizing the concepts of enthalpy and entropy to the individual components that make up a cycle. Okay, so the components of a heat pump for supplying heated air to a dwelling are shown in the schematic below. So I will be drawing the schematic. At steady state, the refrigerant 22 R22 enters the compressor at -5 degrees Celsius and 3.5 bar, and it is compressed adiabatically to 75 degrees Celsius and 14 bar. Now from the compressor, the refrigerant passes through the condenser, where it condenses to a liquid at 28 degrees Celsius and 14 bar. The refrigerant then expands through a throttling valve to 3.5 bar. Okay, the return air from the dwelling enters the condenser at 20 degrees Celsius, 1 bar, with a volumetric flow rate of 0.42 meter cube per second, and it exits at 50 degrees Celsius with a negligible change in pressure. Now, using the ideal gas model for air and neglecting the kinetic and potential energy effects, determine the rate of entropy production in kilowatt per Kelvin for control volumes, including the condenser, the compressor, and the expansion valves respectively. Okay, so what is the cycle here? Let me first draw the schematic of the cycle so that it becomes easier to explain. This is basically a uh, let me start with the compressor. Okay, okay. So it enters the compressor at -5 degrees Celsius, 3.5 bar. Okay, and it exits the compressor to 75 degrees Celsius and 14 bar in the state point P. Now, from the compressor, the refrigerant now enters a condenser. So this is basically the condenser, wherein it will reject heat to some fluid. Okay, and it will lose the heat such that from 75 degrees Celsius to 14 bar and 14 bar, the temperature drops to 28 degrees Celsius at 14 bar. Okay, now from the condenser, the refrigerant enters an expansion valve. Okay, such that there is a throttling of the refrigerant, and due to throttling, the pressure uh, returns to 3.5 bar, then from 14 bar to 3.5 bar, which is the pressure corresponding to the NP state of the compressor. Now it will now pass through an evaporator, thus completing the cycle. In the evaporator also, it will be exchanging heat with some other fluid. uh, okay, so we have been saying that this heat okay, so this is a heat pump cycle in which the mm, air the heat is being supplied, the heat rejected by the condenser is basically supplied to a dwelling space, and this dwelling space, the air from the dwelling space, the cooled air from the dwelling space is also used for the heat transfer of the condenser. So let us suppose that the dwelling air enters at 5 at the state point 5 and it leaves at the state point 6. So what is being stated that the return air from the dwelling enters the condenser at 20 degrees Celsius and 1 bar. So the state point 5 is 20 degrees Celsius and 1 bar for air, and it exits at 50 degrees Celsius and with negligible change in pressure, so it will also be at 1 bar. Okay, and the volumetric flow rate is given as 0.42 meter cube per second. So for this process, we have to determine what is the entropy production rate. Okay, let me draw the process in a TS diagram, TS plot, so that we can utilize this plot for the solution. So basically this is the TS plot in which it basically starts at the point 1, that is the entry point of the compressor, and it gets compressed till the state point 2. Okay. Now it may be isentropic, it may not be isentropic, we do not know that. Okay, so we are just writing it as 2. It may be a straight line, it may not be a straight line. So it comes out at the state point 3, from where there is a throttling. So the throttling will essentially be an isenthalpic process till the state point 4. Okay, so this is the plot of the TS plot of the process. So now here for this solution we consider air to be an ideal gas. So we consider air to be an ideal gas with Cp of 1.008 kilojoule per kg Kelvin. Okay. Now for the compressor, okay, at 1 bar pressure. So what is the inlet of the compressor? The inlet of the compressor is 1 bar, the inlet of the compressor is at minus 5 degrees Celsius and 3.5 bar. That is for the compressor at state point 1, that is minus 5 degrees Celsius and 3.5 bar. The entropy is 0.9572 kilojoule per kg Kelvin. Okay, and at the state point 2, that is uh, 75 degrees Celsius and 14 bar, the entropy S2 is 0.98225 kilojoule per kg Kelvin. So the entropy is not equal to S1. So this line will not be a straight line essentially. This will rather be a line like this. Okay, that is it is basically not a state control, so it is not an isentropic process. Okay, okay. So and correspondingly the enthalpy at this point is 294.17 kilojoule per kg. Now for the condenser, at 3, that is the exit point of the condenser, the temperature is 28 degrees Celsius and the pressure is 14 bar. We have known that close to the liquid condition, the enthalpy and the property values of the compressed liquid are equal to the value of the saturated liquid point corresponding to that saturation temperature. So we can write S3 to be equal to SF at 28 at 14 bar. Sorry, corresponding to that temperature, corresponding to a saturation temperature. That is S3 is at 28 degrees Celsius and 14 bar. This will be equal to the entropy of the saturated liquid corresponding to the saturation temperature of 28 degrees Celsius. So 28 degrees Celsius, and this is equal to 0.2936 kilojoule per kg Kelvin. Okay, now and H3 is HF at 28 degrees Celsius. So this is equal to 79.05 kilojoule per kg. Now for the expansion valve, there is a throttling process, and we have essentially shown in our previous classes that for a throttling process the enthalpy remains constant. So H4 will be equal to H3, that is 79.05. Okay. Now at 4, the 4 will essentially be a mixed state. Okay. So at 4, uh, X4 can be written as H4 minus HF corresponding to state point 4, the corresponding to a saturation pressure of 3.5 bar, and Hg minus Hf. Okay, so 79.05 minus 33.09, and this is HFG, this is 212.91. So this value comes out to be 0.216. Okay, so at 4, the S4 value will be equal to SF plus X4 into SFG. So this is 0.1328 plus 0.216 multiplied by 0.9431 minus 0.1328. So this comes out to be 0.3078 kilojoule per kg Kelvin. Okay. Now considering, so we have essentially determined the entropy values at all the state points. Now considering the condenser as the control volume, okay, so these are all steady flow processes, steady flow devices. Also for a steady, this will be 0 for a steady flow process. This is equal to mass of the refrigerant that is coming. So condenser essentially includes both these, that is the flow of the refrigerant and the flow of the air. So mass of the refrigerant multiplied by the entropy change S2 minus S3 plus the mass of air S5 minus S6 plus entropy generated in the condenser. This implies that the entropy generated, rate of entropy generation in the condenser, is equal to mass of the refrigerant into S3 minus S2 plus mass of the air multiplied by S6 minus S5. Okay, now let us give it number 1. Okay, what is the mass of air? Mass flow rate of the air, that is volume flow rate of air multiplied by the pressure at which it is coming, and RT5. So this is 0.42 multiplied by 10 to the power 5 by 297 into 293. So it nearly comes out to be 0.5 kg per second. And heat loss to air, this is mass flow rate of air, Cp, T6 minus T5. 0.5 into 1.005. Temperature of air changes from 20 to 50 degrees Celsius. That is, there is a temperature difference of 30 degrees. This is 15.075 kilojoules. So this is the heat lost by the refrigerant to the air in the condenser. Now Q air is also equal to Q condenser of the refrigerant. This is equal to mass flow rate of the refrigerant multiplied by H3 minus H2, or sorry, H2 minus H3. Okay, therefore the mass flow rate of the refrigerant is equal to this one, that is 15.075 by H2 minus H3, that is 294.17 minus 79.05. So this value comes out to be 0.07 kg per second. This is the mass flow rate of the refrigerant. And what is the entropy change of air? That is equal to Cp ln of T6 by T5 minus R ln of P6 by P5. But P6 is essentially equal to P5 since there is no change in the pressure of air. So this value becomes 0. So this comes out to be 1.005 ln of 323, that is 50 degrees Celsius, and this is 20 degrees Celsius is 293. So this is 0.098 kilojoule per kg Kelvin. Okay. Therefore, from 1, the entropy generated in the condenser, rate of entropy generated in the condenser is equal to 0.07 multiplied by 0.2936 minus 0.98225 plus 0.5 multiplied by 0.098. So it comes out to be 0.00795 kilowatt per Kelvin. So this is the rate of entropy production in the condenser. So I hope it is clear to everybody. If there is any doubt, you can ask. Okay, so if there is no doubt, then I will move on to the next part of this problem, that is analyzing the same things for the compressor. Now, for the compressor, dSCB by dt is 0, is equal to mass of the refrigerant S1 minus S2 plus entropy generated in the compressor. This implies that the entropy generated in the compressor, rate of entropy generation in the compressor, is mass flow rate of the refrigerant multiplied by S2 minus S1. So this is 0.07 multiplied by 0.98225 minus 0.9572. So this value comes out to be 0.000175 kilowatt per Kelvin. So this is the entropy production rate for the compressor. So for the expansion valve, also this dSCB by dt of the control volume will be 0, that is equal to mass flow rate of the refrigerant multiplied by S3 minus S4 plus entropy generated in the valve. So the entropy generated in the valve, rate of entropy generation in the valve is 0.07 into 0.3078 minus 0.2936. Okay. So this value comes out to be 0.000994 kilowatt per Kelvin. So we have essentially found out the entropy generation rates for the compressor, for the expansion valve, and the condenser. So this can be further extended by calculating the entropy generation in the evaporator. This can be extended to a control volume system which encompasses all the components, that is the entire system, and we can determine what is the entropy production for the entire system. However, I leave it to you for the exercise, because this is just finding out the entropy in the evaporator, and then if we consider the entire system as the, I mean, entire heat pump system, all the components together is the system, or together is the control volume, then some of the entropy generation in the individual components will give the total entropy production. So I hope it is clear to everybody. If there is any doubt, you can ask. Else, we will move on to the next problem. Okay. So okay. So let me start with the next problem. This is quite an interesting problem. So a rigid insulated tank. It is filled initially with 5 kg of air at a pressure of 5 bar and a temperature of 500 Kelvin. Now in this tank, a leak develops and air slowly escapes until the pressure of the air remaining in the tank is 1 bar. So employing the ideal gas model, we have to determine what is the amount of mass remaining in the tank and its temperature. So what is the process here? So it is basically a tank with 5 kg of air, okay, and a pressure of 5 bar and 500 Kelvin. Okay, now a leak develops into it and air comes out such that the pressure inside the tank falls to 1 bar and the mass of air inside the tank is to be determined. Okay, the initial volume of air is what? Considering the air as an ideal gas, it is V1 is equal to mRT1 by, so it is mRT1 by P1. Okay, so let me put in the value. So this is 5 multiplied by R is 287 multiplied by 500 by 5 into 10 to the power 5. Okay, so this volume comes out to be 1.485 meter cube. In the final state, uh, in the final state, the volume of air that remains, the volume of air remaining inside the rigid tank remains same as remains same as V1, that is V2 is V1 is 1.485 meter cube. Okay, so now during the leakage of air, now during the leakage of air, there is no heat loss, and considering the process to be internally reversible, the change in entropy of air, the that is air is the, we are considering the system to be the entire mass of air, so not just the tank, it is the entire mass of air. So there is no heat, other heat transfer during this process. So del q by T, entropy generated, there is no heat loss, there is no entropy generated. If we assume an internally reversible process, then delta S of air is 0. Considering, since we are considering the entire mass of air as a system, there is no change in the mass. Okay, therefore the change in the specific entropy of air is also 0. That is, we can write it as the specific entropy in the first stage is equal to the specific entropy in the second stage. Okay, now for air at 5 bar 500 Kelvin, the entropy is 6930 joule per kg Kelvin, and this is equal to S2. Okay, now from the property table for air, therefore corresponding to the, now this is the entropy, S2 is the entropy corresponding to the final stage, that is when it is at 1 bar. So corresponding to 1 bar and then entropy of 6930, what is the temperature we can determine from the property table corresponding to 1 bar pressure and entropy of 6930 joule per kg Kelvin, the temperature of air at state 2 is equal to T2 is 318.2 Kelvin. Okay, therefore the final mass of air inside the tank M2 is P2 V2 by RT2. So this is equal to 10 to the power 5 multiplied by 1.485 since the volume remains constant, by 287 multiplied by 318.2. So this value comes out to be 1.626 kg. Okay, so the amount of air remaining in the tank is 1.626 kg, and the final temperature of air in tank is equal to 318.2 Kelvin. So this is the answer. Okay, I hope it is clear to everybody. If there is any doubt, you can ask. Else we will move on to the next problem. Okay, so I am taking that there is no doubt, and we will move on to another problem. So it is a problem related to a air compressor undergoing, in which the air is undergoing a polytropic compression process. So an air compressor operates at steady state with air entering at pressure of 1 bar and temperature of 20 degrees Celsius and exiting at 5 bar. Determine the work and heat transfer per unit of mass, per unit mass of air passing through the device in kilojoule per kg if the air undergoes a polytropic process with n equals to 1.3. Neglect the changes in the kinetic and potential energies between the inlet and the exit. Use the ideal gas model for air. So what is the process here? So if we draw the process on a PV diagram, we can express it as, so let this be the 5 bar pressure, and let this be 1 bar. Okay, so this is from 1 to 2, there is a compression process. Okay, it undergoes the compression in the path where PV to the power 1.3 is constant, that is with a polytropic index of 1.3. Now we can say that if we neglect the changes in the kinetic energy and potential energies, neglecting changes in kinetic energy and potential energy, the work done in flow work done in the control volume per unit mass is given by an integration of minus integration of specific volume dp. Okay, this is the expression for flow work for a process undergoing for a flow process, if we neglect the changes in the kinetic and potential energies. Whereas if for a normal displacement work in a closed system, the work done is integration of p dv. Okay, so here where pv to the power n is constant. Okay, so we replace it with minus c to the power 1 by n integration from 1 to 2 p to the power minus 1 by n dp. Okay, so we can write it as minus c to the power 1 by n, and this is p2 to the power minus 1 by n plus 1 minus p1 to the power minus 1 by n plus 1 divided by minus 1 by n plus 1. This is equal to, what is c? C is again equal to, c can be written as p1 v1 to the power n. Therefore c to the power 1 by n can be written as p to the power 1 by n into v. So we can write it as, if we take the minus inside, then it will come out as p1 to the power 1 by n v1 multiplied by p1 to the power 1 minus 1 by n minus p2 to the power 1 by n into v1 v2 multiplied by p2 to the power 1 minus 1 by n, and this is n minus 1 by n. So this comes out to be equal to n by n minus 1 P1 V1 minus P2 V2, and this P1 V1 minus P2 V2 for an ideal gas can be written as R T1 minus T2. Okay, for an ideal gas. Okay, now in this process, we know at the initial state we know the temperature, we know the pressure, but at the final state we know only the pressure, we don't know the temperature. But here, to apply this formula, we do have to know the exit state temperature as well. So for a polytropic process, with air as an ideal gas, then ideal gas T2 by T1 is equal to P2 by P1 whole to the power n minus 1 by n. So this is the formula we already have used in the previous classes, that for an ideal gas undergoing any polytropic process, the temperature and pressure ratios are related in this way. So T2 can be written as T1, that is 20 degrees Celsius or 293 Kelvin, multiplied by P2 is 5 bar, this is P1 is 1 bar, and this is 1.3 minus 1 by 1.3. So this value comes out to be 425 Kelvin. So this is the final exit temperature of air. Now what is the work done in the compression process? So uh, work done in the compression process, okay, per unit mass, this is equal to uh, mm, this is n by n minus 1 p1 v1 minus p2 p2, so minus if we take, so minus n by n minus 1, it will be then p2 v2 minus p1 v1. Okay, just we have taken a minus out, so this is equal to minus n by n minus 1 r t2 minus t1. So this is equal to minus 1.3 by 1.3 minus 1 multiplied by 287 multiplied by T2 minus T1 is 425 minus 293. So this value comes out to be minus 164.2 kilojoule per kg. So this is the specific work input to the compressor for this process. Okay. And what is the heat transfer per unit mass now? For compressor as a control volume, compressor as control volume undergoing a steady state process, dECV by dt, this is equal to 0, this is equal to Q control volume minus W control volume plus M dot H1 minus H2. Okay, M dot H1 minus H2 is the rise in the change in the enthalpy as the from the inlet to the exit of the compressor. So this gives Q control volume per unit mass. This is W control volume per unit mass plus H2 minus H1. So this can be written as minus, we have found it out as 164.2 plus H2 minus H1 can be written as CV 1.005 425 minus 293. So we are considering air as ideal gas. Okay, so in this process it comes out to be minus 31.54 kilojoule per kg. So there is a net heat loss in this process. So this is the work done. This is the heat transferred per unit mass. So I hope it is clear to everybody. If there is any doubt, you can ask. else we will move on to the next problem. Okay, so I'm taking that there is no doubt. Then so we have solved quite a good number of problems related to equipments and devices. Now we will be moving on to a problem related to Rankine cycle, which is a basic working cycle for steam in the steam power plant. Okay, so first we will start with an ideal Rankine cycle. So what happens, how is the cycle and what are the components? We have already used this uh, heat pump cycle, right? So it will essentially just be a reverse of this operation with few modifications, like in place of the throttling valve now there will be pump. So steam is a working fluid in an ideal Rankine cycle. Saturated vapor enters the turbine at 8 megapascal, and let me first draw the what are the components. So there will be a boiler which produces a steam. This boiler, the exit of from the boiler, the steam enters a turbine, which produces a net work output. Mm, this exit of the turbine then enters a condenser where it rejects heat to the ambient, and then the exit of the condenser is passed through a pump which pressurizes it to the boiler pressure. So if we start from the inlet of the turbine, so this is it starts at 8.0 megapascal. So the steam enters at 8 megapascal as a saturated liquid condition, and it exits the condenser pressure, exits the condenser. So exits the condenser at a pressure of 0.008 MPa, like this is P3. Okay, there is a net work output in this. Okay, and there is a work done in the pump, and W net is equal to WT minus WP, and that is given as 100 megawatt. We have to determine the following, that is the thermal efficiency, the mass flow rate of the steam, the rate of heat transfer into the working fluid as it passes through the boiler, the rate of heat transfer from the condensing steam as it passes through the condenser, and the mass flow rate of the condenser cooling water. So there is a condenser cooling water. So how does it reject the heat? So it rejects heat to a cooling water which enters at 15 degrees Celsius and it leaves at 35 degrees Celsius, and the mass of this cooling water is also to be determined. Cycle, if we plot the process on a TS diagram, we will get this. Okay, so it starts from the saturated liquid at the state point 1 in the turbine, which is the point 2. Then it exits as a saturated liquid. Saturated liquid, it exits the condenser as a saturated liquid, and then the pump pressurizes it to the pressure of the boiler pressure, sorry, pressurizes it to the boiler pressure at the state point 4. Okay, so this is the ideal Rankine cycle. Okay, now for this ideal Rankine cycle at at 1, that is 8 megapascal saturated vapor, the enthalpy is equal to of the saturated vapor enthalpy, it will be 2758.0 kilojoule per kg, and the entropy will also be Sg, that is 5.7432 kilojoule per kg Kelvin. Now expansion process in the turbine is adiabatic. Expansion process in turbine is adiabatic without any internal reversibilities. That is, the process is isentropic. This is true only in case of an ideal Rankine cycle, in which there is the process expansion process is adiabatic and there is no internal irreversibility. So in this case, the entropy at the state point 2 is equal to that at the state point 1, and it is equal to 5.743 kilojoule per kg Kelvin, which is less than the Sg corresponding to 0.008 uh, 0.008 MPa. Okay, so the quality can be found out as S2 minus SF by SFG. So this is 5.7432 minus 0.5926, and SFG is 7.6361. So it comes out to be 0.6745. Okay, so the enthalpy at this state is HF plus X2 into HFG. So 173.88 plus 0.6745 multiplied by HFG is 2403.1. So this comes out to be 1794.8 kilojoule per kg. Okay. Now at the state point 3, there is saturated liquid at 0.008 MPa. The enthalpy equals to 173.88 kilojoule per kg, and the pump work so pump is a flow process which increases the pressure from P3 to P4. So the work done will be the specific volume at the state point 3 multiplied by the pressure difference. Okay, so this is 1.0084 into 10 to the power minus 3. This is the specific volume of the liquid phase corresponding to 0.008 MPa. Okay, multiplied by the pressure difference is 8 minus 0.008. This is in megapascal, so 10 to the power 6. So this comes out to be equal to 8.059 kilojoule per kg. Therefore, what is the enthalpy at the state point 4? Enthalpy at the state point 4 is H3 plus the pump work. Okay, so this is 173.88 plus 8.06, that is 181.94 kilojoule per kg. Okay, now we have to determine what is the thermal efficiency. For that, we need to determine what is the power developed, net power developed by the cycle. So power developed by the cycle per unit mass is equal to W net by m dot, that is equal to turbine work minus pump work by m dot. So this is equal to H1 minus H2 minus H4 minus H3. So if we put in the values, we will get this to be 955.14 kilojoule per kg. Therefore, the thermal efficiency thermal efficiency is the net work done by the net heat input. Okay, so this can be written, also written as specific net work done by the specific heat input. Okay, so this is basically 955.14 that we have found out, and this is 2758 minus 181.94 minus 181.94. So this is basically H1 minus H4. Okay, so this comes out to be 0.3707 or 37.07%. So this is the thermal efficiency of the cycle. Okay, the net work done per unit mass is 955.14. The net work is given as 100 megawatt. Okay, and this is in kilowatt, kilojoule per kg. Okay, so what is m dot? M dot is 100 into 10 to the power 3 by 955.14. So this value comes out to be 104.69 kg per second. So 104.69 multiplied by 3600. So this comes out to be 3.77 into 10 to the power 5 kg per hour. So this is the mass flow rate of the steam required. Okay, so this is the mass flow rate of the steam required. Now what is the heat transferred in the boiler? This is equal to m dot h1 minus h4. So m dot is 104.69 multiplied by 2758.0 minus 181.94, and this comes out to be 269.77 megawatt. So this is the heat transferred in the boiler. What is the heat lost in the condenser? This is equal to m dot h2 minus h3. So this is 104.69 multiplied by 1794.8 minus 173.88. So this value comes out to be 169.75 megawatt. And what is the mass flow rate of the cooling water? Mass flow rate of cooling water is the output work of the condenser, because this is the heat that is being carried away, and this is the enthalpy change of the cooling water, that is T out minus T in. Okay, so this is 169.75 into 10 to the power 6 by C for water is 4180. It comes out at 35 degrees Celsius and goes in at 15 degrees Celsius. So this value comes out to be 7.31 into 10 to the power 6 kg per hour. So this is the mass flow rate of the cooling water required. So I hope it is clear to everybody. If there is any doubt, you can ask. Okay, so if there is no doubt, then we will move on to the last problem for today. So in the previous problem, so initially we have considered an ideal Rankine cycle. Now the turbine and the pump, we are considering that both of them have an isentropic efficiency of 85%. We have to determine in this case what is the thermal efficiency of the cycle and what is the mass flow rate of the water, that is the steam required in this case, not the cooling water. This is the mass flow rate of water, that is the steam required in this case. Okay. So initially, in contrast to what we had in the previous problem, here the TS diagram will look something like this. So if we plot something like this, so from state point 1, it was in an isentropic expansion, it was supposed to come at 2s, but now it will come at some point 2. Okay, From 2 to 3 it is same. Then from 3 to 4 it was supposed to be something like this, but it will go something like this. 4 and this is 4s. Okay, so this is the cycle, this is the change in the cycle. Now from the previous problem we have already seen that H1 is 2758.0 kilojoule per kg. H2s, that is considering, and H2s is equal to the enthalpy considering an isentropic expansion process, so that comes out to be 1794.8 kilojoule per kg. Now isentropic efficiency of the turbine is equal to H1 minus H2s by H1 minus H2. So what will be H2? H2 is H1 minus isentropic efficiency of the turbine multiplied by H1 minus H2s. So this value, if we put in the values, we'll get this to be 1939.3 kilojoule per kg. Okay, again H3, that is equal to HF at 0.008 MPa, that equals to 173.88 kilojoule per kg. Okay, now isentropic efficiency for the pump is the pump work isentropic by pump work actual. So the actual pump work is equal to the isentropic pump work by isentropic efficiency of the pump. So the pump work actual is, we have found out the pump work isentropic pump work to be 8.06. So 8.06 divided by the isentropic efficiency of 0.85, so this value comes out to be 9.48 kilojoule per kg. Okay, now therefore H4 here will be equal to H3 plus pump work actual. So this is 173.88 plus 9.48, which is equal to 183.36 kilojoule per kg. And therefore, the net work output per unit mass is H1 minus H2 minus H4 minus H3. So putting in the values, 2758 minus 1939.3 minus 9.48, so this comes out to be 809.22. This is kilojoule per kg. Okay, and Q input per unit mass is H1 minus H4, that is 2758.0 minus 183.36, so it comes out to be 2574.64 kilojoule per kg. Therefore the thermal efficiency is W net by heat input. So this is 809.22 by 2574.64, so it comes out to be 0.3143 or 31.43%. So in contrast to where it was an ideal, that is isentropic case, the thermal efficiency decreases from 37% to 31%, that is there is around a 6% decrease in the thermal efficiency in the actual case. Now again W net per unit mass is 809.22. So mass flow rate of the steam is 100 into 10 to the power 3 by 809.22. So this comes out to be 123.57 kg per second, that is 123.57 into 3600 kg per hour, or 4.449 kg per hour. So you can see that the if, in the actual case, the mass flow rate of the steam required for the same power output increases from 3.77 into 10 power 5 kg per hour to this will be, sorry, into 10 to the power 5 into 10 to the power 5 kg per hour. So the mass flow rate of the steam required for the same power output also increases. So I hope this is clear to everybody, and the basic working of the Rankine cycle is also clear. So if there is any doubt, you can ask, else we can close today's session. Okay, so I'm taking that there is no doubt. Okay, so let us close today's session then, and I hope to see all of you in the next session on next Friday. Okay, so thank you for joining.